All right, in this video, we're going to solve this truss. We're going to show how to solve just the external forces, and in a following video, we will show how to solve the internal forces. So we're going to solve using these steps. First, we have to determine if it's statically indeterminate, draw the free body diagram, and then solve for the external reaction forces. So the first thing we want to do is solve to make sure that it's statically determinate to see if we can actually solve the truss. Okay, so we're going to have 2j equals m plus r. So j is the number of joints. So joint A, joint B, joint C. So we're going to have 2 times the 3 joints. The members are the beams between the joints. So there's member 1, member 2, member 3. And then the reaction forces, remember there's 2 on a pin, 1 on a roller. So there's 3. So this says 6 equals 6. Good. So this is statically determinate. And now we can move forward with this truss. So now I'm going to draw the free body diagram. On the free body diagram on a truss, you want to draw the truss. You want to put all the forces on it. So we have the load, which is the 50 pounds. Okay, we have our reaction forces. Remember, there's 2 on a pin, one that is perpendicular to the surface. Now the surface is a wall. So we have the one that's perpendicular to the surface. We have the one that's parallel to the surface. Remember, you can pick these arrows whichever direction you want. I tend to just go right and up. Okay, and then with a roller, we only have one that's perpendicular to the surface. Now this was joint A, joint B, and joint C. So this is a reaction force. It's at joint A, and it's going in the X direction. This is a reaction force. It's at joint B, and it's going in the X direction. This is a reaction force at joint B, going in the vertical Y direction. Okay, when you're doing a free body diagram for a truss, you also want to put in any dimensions or units that you might have. Okay, so those are both 3 feet. 3 feet and 3 feet. We know these are 45-degree angles. Okay, at this point with external, we don't need that. We will need that when we do internal forces. So that's step 2. Okay, now we want to solve for these 3 external forces. So this is step 3. In step 3, it says first we want to solve using the sum of the moments. We have 3 equations we're going to use. We're going to use the sum of the moments is equal to 0. The sum of the forces in the X direction must be 0. The sum of the forces in the Y direction must be 0. These are our static equilibrium. Okay? This is the translational equilibrium, and this is the rotational equilibrium. We always want to start with this moment. So we're going to start with the sum of the moments is equal to 0. But where are we going to sum the moment? A moment has a place where it's going to rotate, like a fulcrum or a hinge. We're going to put that at the place where it gets rid of the most unknowns. We're going to put our moment at joint B, because now these 2 reaction forces go straight through there, and so the force doesn't matter what it is because the distance is 0. Okay, so the moment will become 0. So that means we can ignore these 2 things for the sum of the moment equation. So for the sum of the moments around joint B, we're going to have this reaction force A. Okay, and reaction force A is going to cause me to go in that direction, right? If I push, it causes me to go around in a counterclockwise fashion. Since we're going counterclockwise, our direction is a negative with counterclockwise. Okay, I'm sorry, a positive. Clockwise is negative, counterclockwise is positive. So we have positive. So we're going to have the force, RAX, times its distance of 3 feet. Okay, and that's going to be in positive because it's counterclockwise. Now we have this next one here. This load is going to cause me to turn this way, right? When I here and push down, it causes me to go clockwise. So this one is a negative. So now I'm going to make this a negative, or a plus, a minus, which is just a negative. And we're going to take the force, 50 pounds, and we're going to multiply it. Now we want to go the perpendicular distance. It's not like 3 and 3, and it's not across here. It's the perpendicular distance, right? So this guy, it's like he's here. What's the distance from this point? In a perpendicular fashion is just the 3 feet still. And so now I have this equation that the force times the distance minus the force times the distance has to be equal 0. So if we take this is 150, right? So we're going to add 150 to both sides to get rid of this term. So we're going to add 150 to this side, and we're going to get that the reaction force in the x direction at point A times 3 is equal to 150. Divide both sides by 3, and we get that the reaction force in the x direction is going to be 50 pounds. So we know this reaction force right here is equal to 50 pounds. And because I got a positive here, that means I guessed right with going, I guessed correct with going right. Okay, now I'm going to use the sum of the forces in the x and the y direction. It doesn't matter which one you start with. Okay, so we'll just start with x because he's next on the list here. So the sum of the force in the x's must be 0. That's equal all the forces go in the x direction. So any arrows going to the right. So it's going to be RAX, and they're both going to the right, so they're both positive. And RBX. We know RAX is 50. So we can solve this, and we can say that RBX is equal to negative RAX, right? Because we have to subtract RAX from both sides to get rid of it. Well, we know RAX is 50 pounds, so this is negative 50 pounds, which is equal to RBX, right? Now, what does it tell me? The negative says, oh, I was wrong. It's not going this way, so I'm going to cross out that. It's better if you do this on pencil. I don't have colored pencils. So my 50 pounds now is going to the left, so this is wrong over here, okay, which is okay. Now we kind of ignore this 50 now. I mean this negative on the 50. We just know it's 50 pounds going to the left. That's what the negative told me. It's going opposite of what I guessed. Okay, now we're going to sum our forces in the y direction. They're also 0. In the y direction, I have RBY going up. I have the load, 50 pounds, going down, so it's a negative 50. So that means RBY is equal to 50 pounds, right, when I add the 50 to both sides. So now I know, and it's positive, so I guessed right. And so now I have all my external forces, and they're all solved, okay? So I have RAX, RBX, and RBY. And they all turned out to be 50, which is just kind of a coincidence. All right, that's basically it for external forces. In the next video, we will use this information to solve for the internal forces.